Thank you for making time this afternoon, if it's the afternoon for you, to attend this webinar. I'm Chris Noble, so I'm a senior engineer here at Verist, and this is my webinar regarding testing and modeling anisotropic polymers for better FE simulations. So about me, I'm a senior engineer at Verist. My expertise is in solid mechanics simulation and experimental mechanics of soft tissues. Prior to my role here, I was a senior scientist in the biomechanics team at Vertex Pharmaceuticals. And I was a postdoctoral research fellow and research scientist at Mayo Clinic prior to that, where I was awarded the K99 R00 Award and the Internal Career Development Award at Mayo Clinic. My research specialized around arterial and valvular mechanics. I got my PhD in mechanical engineering from the University of Sheffield in England, and that was under the supervision of Dr. Zeke Taylor. And I got my master's in engineering, in biomedical engineering from the University of Sheffield as well. I've got several peer-reviewed journals, manuscripts in biomechanics journals, including the Journal of Mechanical Behavior of Biomedical Materials and the Annals of Biomedical Engineering. So to give a bit of a background at Verist, we were founded in 2006. We're headquartered in Needham, Massachusetts. Currently have 12 technical staff, 80% of which are PhDs. We have a 3,000 square foot mechanical test lab. And it's important to note that Verist transfers all methods, models, and data to our clients. And that includes the IP. All IP that we generate as part of our engagements belongs to you, the client. A bit more about us at Verist. We like to say we provide engineering expertise to help you create extraordinary products. So to do that, we're accelerating product development and innovation by solving our clients' toughest challenges. Our PhDs have subject matter expertise in engineering mechanics, material science, chemical engineering, and electromagnetism. And again, there's another thing we like to say is we bring academic experience on an industrial timeline. So to dig right into it, when we see anisotropy in polymers, we've seen them either in biological materials or in synthetic materials. And in biological materials, the major sources of anisotropy are fiber reinforced ECMs. So in this case, it would be things like arterial walls. It would be pericardial tissues, skin tissue. And then we've got the anisotropy coming from cellular organization. So think about muscle tissue and the muscle cells providing mechanical strength and that anisotropy. There's oriented natural rubber. And then silicon natural fibers as well provide anisotropy. In polymers, it's a bit more varied. For instance, fiber reinforcement is a large part of it. Carbon fibers, sort of like that. The actual base resin is a polymer. We've got process-induced molecular orientation. Classic example of this is PTFE, Teflon, and expanded PTFE, where you have different mechanical properties depending on whether it's in the machine direction or cross-machine direction. And that basically changes the cross-fiber density. And then we have the crystalline morphology of your polymer, which can dictate the orientation of the polymer fibers and therefore the polymer chains and therefore your mechanical anisotropy. You have reinforced fillers with a preferred orientation. So if your polymer has some sort of filler in it, if that filler is is more aligned in one direction than another, then that will create anisotropy. Foams are a great example of anisotropy in both compression and tension. If you have a directional cell structure in your foams, you will get anisotropy. Residual stresses and thermal history, depending on how the polymer is actually manufactured, you can bring in anisotropy in there because of your residual stresses. And then woven and fabricated structures are a classic example as well. So your fabrics and the like. So the main loading types for planar samples that we tend to use for calibrating constitutive models are uniaxial tension, compression testing, shear, and biaxial tension. And to say these are really the four main ones we would use to calibrate a constitutive model and to investigate planar behavior. There are other tests, but they're a lot less common. So one of the main things for anisotropic testing is that quite often uniaxial tensile testing isn't enough. So performing a uniaxial tensile test in one direction certainly will be insufficient because you're not probing that difference in mechanical behavior, that directional mechanical behavior. We recommend testing at least two orthogonal directions, preferably aligned to the material principal axis if it's transversely isotropic. So the image on the right shows what happens if you don't do that. So this is at a 45-degree angle. This is with a Holzhofer gas Ogden material model, which for those unfamiliar, I will talk about more later. But this is an anisotropic constitutive model. And we provide a 45-degree fiber angle. And we can see the test in the two, I think in a stiffer and more relaxed and more compliant material. And we can see that basically what's happened is that you've got some basic shear loading going on there and some large deformations that aren't in along your test axis. And so it really shows how you have to be careful when you're orienting your sample for in uniaxial tension. If you have orthotropic behavior, then you have to be even more careful. If there's symmetry to your orthotropic behavior, so you have two families of fibers that are symmetric about an axis, it becomes simpler. You can often test around your axes of symmetry. But if not, then you have to be very careful how you're setting up your experiment. Strain should be measured in both principal directions in a uniaxial test. In Varist, we use digital image correlation to do this. You can use fiducial markers, although you do lose some accuracy that you have with DIC. But if you have to do things such as in a submerged bath, in temperature or anything like that, which would disturb your DIC speckle pattern, then fiducial markers become necessary. Additional data such as shear testing is recommended for model calibration just to make your model more robust. And if coupling between principal directions exists, you cannot use uniaxial testing alone. It's worth having in there if you have the time and material to do it, but really you need some form of biaxial testing to capture that coupling. And also, this extends to viscoelastic behavior in that you cannot just use a single quasi-static test. You have to perform testing at multiple strain rates and preferably cyclic loading as well. So now I'm going to go into a little bit more of the biaxial test methods and sample types, just to give a breakdown of the major biaxial test methods that you can employ. So to give an introduction to biaxial testing, in general, it is that the sample is pulled in two orthogonal directions with force measured in each direction. Sample mounting is more complex than uniaxial testing, and it can get considerably more complex as you try to reduce the effects of boundary conditions or boundary effects. To fully characterize the anisotropic response, multiple loading ratios need to be run. So preferably you need equibiaxial and at least two other loading ratios in each direction. So you'd need to run something like 1 to 3 loading ratio in both directions at a minimum, preferably more than that, to really characterize your anisotropic response. To characterize viscoelastic response, further rate-dependent and cyclic loading will be required, as within uniaxial testing. And then on the right, you see the most common mounting types, which we'll go into a bit more later. So we have clamps, sutures, and rakes. And the clamps can be applied on a cruciform or a square sample, and we will talk about the advantages and disadvantages of that later. And for all geometries, it's difficult to test to failure due to the stress concentration. So regardless of your mounting method or your sample shape, testing to failure is very, very difficult because if you're using sutures or rakes, they're going to fail at those attachment sites. And if you're using clamps, more than likely your stress concentrations are not going to be in your area of interest. And so you're not going to capture that failure behavior accurately. So for cruciform specimens, these are relatively simple to mount and run compared to other biaxial methods, particularly if this is quite a stiff sample. You can mount this pretty easily, all things considered, because it will hold in place quite nicely. If it's quite a compliant elastomer, it's going to get a little bit more difficult, but it's certainly still easier than many of the other biaxial methods. You do need a large amount of material in order to cut this into your required geometry. And under high extension, the effects of the boundary conditions dominate, and that leads to the poor load transfer to the specimen, and I'll show that in the next slide. This can be mitigated somewhat by using more complex cruciform geometry, so rounding off edges, but you will have to be careful there as well, as I'll show later. Sample deformation is restricted in this test compared to an ideal biaxial test, and that basically leads to resulting in artificially stiffer behavior. So if you calibrate a constitutive model to this and assume basically ideal planar biaxial conditions, you have an analytical solution that you're calibrating to, you will generate a stiffer constitutive model than that is in reality because of the constricting of the sample and this artificial stiffening effect. This effect is amplified by having shorter arms on the sample because, again, you're just constricting that motion more. And it can be somewhat mitigated by cutting slits into the sample arms. So you see in the image on the bottom right. And again, that's just freeing up motion of the sample. So the sharp corner cruciform sample is shown here. So this is just a quarter symmetry, Holzhauer-Gasser-Ogden material model with fibers aligned in the y direction. We have an equal biaxial load of 0.125 newtons. And the stiff model basically has these stiffness-like parameters in the Holzhauer-Gasser-Ogden model. So your mu, your K1, 10 times greater than the nominal model. And this is ready to demonstrate this concept I'm talking about in the third bullet point, that under high extension, the effects of the boundary conditions dominate. And we can see that here, that in the nominal that's more extensible, if you actually look at the central region of the sample, so this bottom right-hand corner, which will be the central region in a full sample, you can see that the strain field is hardly different, even though the extension is considerably more. So all that stress is shifted to the arms, and you've got a large stress concentration spreading out in that corner region. So you really have to take care when testing to high strains or using very extensible materials that you want to test to those high strains with this test type. For rounded corner cruciforms, you'd expect this to try and mitigate some of these stress concentrations we can see in this model here. However, what I've done is deliberately designed it with less desirable characteristics. So our arms are quite short and stubby, so they have a poor aspect ratio. They should be longer and thinner. And so what we're getting is actually worse stress concentrations in our sample. We're finding a less uniform stress field and lower magnitude stress in the central region. And so we're actually getting any better result than we would with just a simple sharp-edged cruciform. So it really has to be carefully designed. So the next one I want to talk about is a clamp sample. And there are a few advantages to this. It is relatively simple to mount and to run the test. It needs less material than a cruciform sample. However, the big issue with clamping is that there is a poor load transference to the specimen, and larger samples can help mitigate this. But then if you compare that to, say, the cruciform, then by the time you get large enough samples to mitigate this, you're likely using the same amount of material as you would in a cruciform. So your advantages slowly begin to disappear. Again, we're looking at this stress field again in a quarter symmetry model. So in the bottom of the screen, there's this of the image before, just cut in a quarter to show what we're looking at. And again, it's 0.125 equibiaxial load, and Holzhauer-Gasser-Ogden material. And the stiffer model is approximately 10 times stiffer than the nominal. What we've seen is a very poor stress field regardless of the sample stiffness. It's certainly worse in the more compliant material at the higher strains, but it's still not ideal in either sample. And you can see that you really need quite a large sample to make this work. Again, this also makes testing to failure very difficult because your stress concentrations are going to be at those clamps. You can round the corners to help mitigate this, but still, it's going to very much be concentrated around these clamps. Another example to look at is hook or suture loaded samples. This is kind of the opposite of the other two in that it provides much more freedom to the sample. So you don't, you have minimal boundary effects, no shear stresses are transferred onto the sample. And as a result of that, it's very useful when the material axes of anisotropy or fiber orientations are not known. But it is difficult to apply and apply consistently with the correct spacing and consistent locations, which is important. If you've got bad spacing locations and inconsistent, then you're going to disturb your strain field and stress field, which could lead to variation in your data and your calibrations. You cannot apply large loads to this. It's quite simple. If you apply large loads, you're just going to rip the sutures straight out. And so you really are restricted to quite small loads with this. An alternative is using rakes. The difference between sort of the rakes and the hooks and sutures is that the hooks and sutures are basically a rope with a hook on the end. It's a suture. Whereas the rakes are rigid metal rods, small ones, with hooks on the end. And so what the advantage of this means is that they're rigid, so you can easily, if you line them in place ready, you can place a sample on top and mount it very easily and consistently. The disadvantage of that is that the hooks will transfer load under shear, and so you get this artificial stiffening effect because of that. It's not as strong as it is with clamps or with cruciform, but it's still present compared to hooks and suture. And so you have some problems when you have a poor sample alignment. Some testing system manufacturers actually provide the tools to assist in the sample placement and will provide their own rakes as well, which makes this considerably easier. It is still time consuming to run compared to a cruciform test or a clamp test, or certainly a uniaxial test. And you can't apply large loads again because you'll just rip them straight out. So just to give an example stress field for hooks or sutures, hooks versus sutures, hooks, sutures versus rakes. In an ideal case, in this finite element model, where we have we've got a transversely isotropic material, the fibers are aligned in the y direction, and we've got an equal biaxial load of 0.5 newtons. Quarter symmetry's been used on the rakes model that we've then expanded out into a full model, and the mechanical properties correspond to the previous slides, the nominal, more extensible case. And so what we can see is that we have near identical stress fields in each one. So if you know your fiber orientations, there is very little advantage of sutures versus rakes in an idealized case. Obviously, in a real sample, you probably are going to still see some degree of shear that is going to be giving some artificial stiffening, but with careful design, you can minimize that as much as possible. And the rakes really do improve your test speed and test consistency, and that consistency is likely more important. I'm just going to take a break here and have a drink, sorry. So the next thing I'm going to talk about is the sample alignment considerations, which I've alluded to earlier on. So, as we know, anisotropic materials respond differently depending on the loading direction relative to fiber orientation or the axis of anisotropy. Synthetic materials usually have a known orientation, but biological tissues quite often do not. A good example of this is pericardial tissue. It has a large variation in its fiber orientation as you go around it, and sometimes it's not always clear where that fiber orientation is. And so mistakenly, you can mount a sample and not know the fiber orientation as well as you would like. Misalignment during mounting often means that the applied loading no longer matches the assumed material directions, and that distorts your results. So the next slide, I'm just going to show some simulations of where the sample's misaligned to give you a picture of how this can affect your test data. So in a cruciform sample, this is a whole Holzapfel Ogden model. We've got an equal biaxial load of 0.5 newtons, and we've got a fiber orientation of 45 degrees. This is in the extensible nominal case we saw previously. And what we can see is that the stress is purely concentrated on the arms and a little bit in the corner regions. And hardly any is in the central region of interest that we actually care about. And so this is far from ideal, obviously. And so therefore, it really shows that for a cruciform sample, you really have to be careful aligning your material to the principal axes of your anisotropy or your fiber orientations. And if you've got something like orthotroping, you have to be careful designing it. Again, it would very much depend on case-by-case basis. But as a general rule, if you've got a fiber reinforced material, and you've got two symmetric families of fibers, making sure that the axis of symmetry is aligned with one of your principal directions of your test is very important. So if we look at hooks and sutures versus rakes, again, it's a 45-degree fiber angle. We've got an equal biaxial load of 0.5 newtons. The way this model has been formulated is the rakes are allowed to have some shear, but that shear will come with the restrictions of the rakes in that you're basically going to get some tension and compression as a result. Both perform better than a cruciform specimen, but the rakes begin to have a lot of sort of stresses, not in that central region that we're interested in, whereas the sutures in that central 25% region, which I'll go into later, you get a much better stress field, a much more uniform stress field. So for strain measurement, as many people probably are aware, but not everyone, if you're performing a uniaxial tensile test on a sort of ASTM type 5 dog bone, for instance, you really want to be recording your strain on that gauge region of your dog bone, because often the machine crosshead displacement, if you just took the starting crosshead displacement and then divided by the end crosshead displacement to get your stretch, you'll greatly overestimate how much that gauge region is actually deforming. And the same applies here as well. So and you can see that on that cruciform sample quite clearly, that a lot of the displacement that's being applied in that equibiaxial loading is being transferred to the arms. But we can even see it with this rakes model below, where basically we've got a 10 by 10 rake alignment, and then we've got a deformed distance of 17 millimeters. So if you took that by raw machine head crosshead displacement, you'd have a strain of around 0.7. The actual strain, though, in that region is around 0.54. So you really need to make sure you are recording the strain in the central region of that sample by other means. One common means is by measuring strains using optical techniques, such as tracking fiducial markers or digital image correlation. So to delve into that a little bit further, markers should be placed in a regular square pattern. So if you're using fiducial markers, they should be placed in a regular square pattern within the central 25% of the sample. However, if you've got a rake or hook suture system that covers the sample edge as well, and you've got good alignment of your fibers, and you know that your strain field is going to be pretty uniform, then you can have an array larger than the central 25% to give a better signal to noise ratio. The strains are then calculated using finite element shape functions according to the array size. So 4 to 5 dots would give you a linear shape functions, whereas 9 dots gives you quadratic. This has got a 9 dot over on the right. It just gives you better basically strain interpolation between your dots. DIC can be measured across the whole sample, but it's important to measure in that central region I just mentioned when you're actually taking your strain measurements. The reasons, again, for using fiducial markers over DIC would mostly be because of your experimental setup. If you're testing in a tissue bath or anything that would disturb your DIC speckle pattern, you really want to be using fiducial markers instead, just because of the consistency of it. If you've got a disturbed DIC speckle pattern, or you say you're in a bath and it gets disturbed, and then you get floating particles going over your image, that will greatly harm your DIC image. Okay, so 1 second to wet my throat. So now I'm going to delve into other methods for biaxial testing. These don't really follow either the uniaxial testing or dedicated biaxial testing. They're more different methods for specialized scenarios. So for biaxial tension for a cylinder, you can actually get a good biaxial state with a closed form solution just by basically pressurizing it and letting it inflate, and then recording the deformation. DIC is a great way to do this. As it expands and you get the deformation, you basically have a form of stress strain curve that you can calibrate to pretty easily. And this is particularly advantageous for blood vessel testing, such as arteries, because then you don't lose the residual stress in the tissue that you get if you cut open and lay it flat. Another form of sort of inflation testing is bulge testing. This basically, you have a ring of you have a circle of material, and you pin it down between two rings, and then you inflate underneath that material. You could also use a spherical indenter of a similar geometry. Again, the important thing is to get this spherical cap approximation, which is a closed form solution. Inflation gives the advantage that you will almost certainly guarantee to get that. Excuse me. You're almost certainly guaranteed to get that, and you don't have to worry about frictional effects. But a indenter will also work if you can minimize those things. And so for isotropic materials, you will get a closed form solution to this. For transversely isotropic materials, the fibers must be aligned circumferentially, which is quite difficult to achieve, but that will give a semi-closed form solution. And for orthotropic materials, it's actually better than transversely isotropic, as if you have two equivalent symmetric fiber families that I've talked about previously, and they are uniform over the surface of the material, a semi-closed form solution also exists there as well. The reduced boundary effects allow these tests to be run to failure. There are a couple of caveats to that. So if it fails not basically at the boundary, then that's going to be due to boundary effects, so you have to discard it. And if the failure leads to a non-spherical shape, then that closed form solution or semi-closed form solution will begin to break down. And then it's really up to operator discretion to at what point you choose to start, say, this has gone too far past the closed form solution, where we are now making our assumptions are too strong. Another approach you can do to actually, if you've only got a uniaxial tensile test machine and you want to get a biaxial stress state in your material, another method to do this is to basically build a cruciform sample out of your specimen, and then have it so that the uniaxial tension will pull it on both of the arms at the same time. This has a couple of advantages that I'll go into later, other than the ease of testing. The one major disadvantage of it is that the stress states are not as uniform as true biaxial loading, and there's no closed form solution. And so you need inverse FEA to calibrate the constitutive model. An example cruciform sample is shown on the right, and that's been designed with FEA to yield biaxial tension. This is from a paper. One thing to note with this design is that altering the angle of the cruciform will change the loading ratios, but that vertical angle alpha must not approach 90 degrees. And that's to avoid a shift between major and minor strain directions at the early stages of deformation. And that's due to plane strain compression along the horizontal direction. So looking at this further with an FEA model, this shape, the paper we took this shape is from Bellet et al. Material parameters are the same as in the previous simulation. So this is a whole sulfur gas Ogden material. It has the same material parameters as the nominal cases shown previously. Samples with fibers loaded perpendicular to the loading, so 0 degrees, show considerable lower stresses, and the maximum principal stress vectors are strongly aligned with the ligaments. However, sort of counterintuitively, if you have the fibers oriented along the axis of tension, you'll actually end up with load parallel to the loading direction, but you have really high stress concentrations. And the maximum principal stress is less well aligned with the ligament, so it's not ideal. However, if you then begin to orientate your fibers along this along these ligaments, these arms of this cruciform, you begin to get a better biaxial stress state. The stresses are concentrated in the ligaments along the ligaments, and this is basically becoming equivalent to a large loading ratio in a biaxial test. So sort of like a 5-to-1 loading ratio. And so you can see that by basically tailoring that alpha angle and tailoring your specimen orientation with respect to its fiber orientation, you can begin to alter your biaxial stress state and therefore get your loading ratios. Another alternative specimen design is this one from Sampow, 2024. And this has more rounded edges. Again, we're seeing a very similar behavior though. So in the 0 degrees, we're seeing a more distributed stress pattern. And we're seeing it more aligned with the arms, the ligaments. And then if we have it at 90 degrees, then we have it, we have very, very concentrated stress pattern. With fibers aligned at 45 degrees, sorry about this. With fibers aligned at 45 degrees, stresses are concentrated in the ligaments, again along the fiber direction. And this is equivalent to a large loading ratio in a biaxial test again. So it's very similar. The stress contours are slightly less uniform. They have a lower magnitude, but you have a more gradual transition. And so it really depends on what material testing in the individual experiment you want to run, whether the two geometries, which one works better for you. Obviously, the prior one, you can control those loading ratios better. But this one, you get that more gradual transition, which may be better. So here's the table, just quickly, giving the rankings of the individual test methods with respect to 6 major considerations. These aren't all of them, and depending on your individual tests, these values may go up and down a little bit, and also there may be other factors you want to bring in as well. But in general, for a lot of applications, this table is what we think is a general recommendation. So max accurate strain, what that means is how much you can pull the sample and still have a good strain field. So for cruciform and clamps, this is quite weak. We don't get a very good strain field at high stress field at high strains. For hooks and sutures, we get it better, but it really can't go to those high strains very well before you start to get tearing, and therefore you start to lose your load isn't transferred as well. Bulge inflation really is the best for this though, because you can go virtually all the way up to failure. And it's quite a long way the best for this application. The uniaxial approach works well because you can pull it quite a long way, and you can get a uniform strain field depending on how you orientate your sample with respect to your fibers and how you adjust that specimen dimensions. So strain stress field uniformity is basically in the best case scenario for that test. So at say 10% strain, how uniform is the stress field? For cruciform, it's pretty good. It could be better, but it does work. For clamps, it's still poor. There's no way of getting around that. You have to have quite a large specimen before you begin to get anywhere near a uniform stress field. For hooks and sutures and for rakes, it's very, very good. Rakes is a little bit lower just because of that shear stress transferal. Bulge inflation, this really varies quite extensively by the type of specimen you're testing. And then for uniaxial, it's somewhere in the middle between the cruciform and the clamp. You really need to use DIC on this test. For material efficiency, the cruciform is obviously very bad. So is the uniaxial on the other side, both sort of from the same problems. Uniaxial is a little bit better. We can get away with smaller samples. The clamp is pretty great. It's one of the few advantages of this method in that you can have quite small samples. However, you are going to sacrifice accuracy in your strain field and stress field as a result of that. Hooks and sutures and rakes are probably the best for this by quite a margin. You can test really quite small samples. I've tested 5mm squares using this method on the rake system. Bulge inflation can be pretty good depending on how what your setup is. If you can get a small enough ring and you can still create that dome appropriately, then bulge inflation works very well. In terms of ease of adoption, it's very split here. The cruciform and clamp, they need specialized test equipment. They need a biaxial tester, and they need some degree of expertise, but not as strong as the expertise required for hooks and sutures and rakes, which really ranks them the lowest. For bulge inflation, it's sort of in the middle because it is easy to use in a dedicated biaxial test system. It's certainly easy to build if you want to build one yourself, but it comes with that difficulty of how to set up your test appropriately. And then uniaxial is probably the easiest, even though you have to do this geometric variation, you have to run DIC. It still has the far easiest adoption. Most test labs have a uniaxial tester. In terms of load ratio control, all the biaxial test systems, whether it's cruciform, clamp, hooks, or rakes, are obviously excel at this. This is what they do. Bulge inflation is very, very poor at this. It's very, very hard to control that and keep your analytical solution intact. Uniaxial is slightly better, simply because you have that ability to vary it by your angle and your angle alpha and with respect to your fiber angle as well. For stiff materials, hooks and sutures and rakes obviously do not work. You cannot puncture it, and even then, if it's very stiff, it'll start to get comparable to the stiffness of your sutures or your rake tines. Bulge inflation is also not great for this. If you think about it, to get the higher pressures required to get that doming, you're getting very, very high pressures. You're in risk of generating projectiles if it breaks. So it's not ideal. I would not recommend using bulge inflation for this. If you're using a spherical indenter, possibly better, but then your frictional effects begin to become a problem then as well. For this, your cruciform, your clamp, and your uniaxial test really come out on top, simply because of the ability to clamp that sample and hold it in place. So further testing considerations, if you give me 1 second. For shear testing, what we do is something called a planar shear test, as this is very simple to implement. For small strains, this approximates a pure shear state, and similar tests have been used to calibrate anisotropic hyperelastic materials previously. These tests only need a fixture on a standard uniaxial test system. And for anisotropic materials, you should really test in multiple orientations, as you would in a uniaxial tensile test. So for transversely isotropic materials, at least perpendicular and parallel to the fiber direction and at 45 degrees. We also recommend using DIC to verify constant strain. Additional testing modes. So many biological materials, such as synthetic woven materials and synthetic woven materials, such as fabrics, have an assumption that the fibers do not contribute to compressive loading. And so for these, isotropic compression testing is really only used to characterize the so-called bulk behavior. However, for many synthetic fiber reinforced materials or synthetic anisotropic materials and foams especially, that assumption does not apply, and the anisotropic behavior has to be characterized in compression as well as tension. Although that is varied by your use case as well. If you're only using the thing in compression, you can likely get away with characterizing only the compression. For materials, for such materials, similar testing protocols, uniaxial testing for anisotropic materials, as I said, apply. But you may want to use additional tests such as V-notch shear tests as well. One particular final thing to note on testing is for biological tissues, and that is preconditioning. Biological tissues in situ are mostly under periodic loading. So if you think of blood vessels in the cardiac cycle or muscle and tendons during ambulation, they're constantly being loaded and unloaded. When they're removed from the body, they show some degree of mechanical recovery. And so the stress strain behavior becomes stiffer than what you would see in situ. Preconditioning applies cyclic load into the tissues to try and restore it back to that in situ condition, so you're getting a representative stress strain curve when you do your calibration. Preconditioning protocols do vary by tissue type though, and it's worth looking up for your particular tissue. So for cardiac tissues, it's common to use 10 cycles at quasi-static strain rates. But for tendons, that can become a lot more cycles. So now I'm just going to go quickly over three common, well, two common and one more uncommon anisotropic material model. Give me 1 second. And so these two models, the common ones we're going to discuss are the strain-based Fung model and the invariant-based Holtz-Apfel model. We're also going to talk about another strain-based model, the 8-chain model, the Bischoff model, and how that really differs to the other two in terms of its formulation. So the Fung anisotropic hyperelastic model is probably the most common used strain-based model. It can be written as this equation below for the strain energy function. The right term is just basically the volumetric behavior. So we're not really as interested in that. What we're really interested in is this first term. So you C is like a stress light parameter. And then we've got this exponent raising Q. And Q is basically a double contraction of the isochoric green tensor on either side of this B tensor, this fourth order B tensor. And this fourth order B tensor is very similar to an elasticity tensor. And so in the same way that you can simplify an elasticity tensor down to transverse isotropy or orthotropy, you can do the same with the B tensor. And this model is available in many commercial FE solvers. For instance, it's available in Abacus, certainly available in Abacus to my knowledge, and probably many other ones such as ANSYS. This is a very common model. Holtz-Apfel type models. The compressible Holtz-Apfel-Gasser-Ogden model is one of the most commonly used biological tissue models out there. There are many variants. People have done various iterations on this. The one I'm showing here is from Gasser 2006. And the way this is formulated is that you have your strain energy function. Again, it's a compressible one. So you have your volumetric term as your last term. Then you have your two isochoric terms. So you've got your isotropic ground matrix portion, which is commonly expressed as a neo-Hookean model. And then you've got your fiber term, which we'll delve into more. The fiber term has three main parameters. There's your K1, which is like a stiffness light variable. And then there's K2, which is kind of like a scaling variable. And then within, and then that multiplies basically to your fiber contributions. So you have this sum over the number of fibers you've got, and this exponent that raises basically K2 and this EI variable. And this EI is basically describing your fibers. So the way it's formulated is that you have this sum of basically I1 and I4 for your fibers. And kappa is basically governing how with a mixture of those two terms. So if kappa is 0, then you have a no dispersion, is fully I4. Whereas if kappa is the third, then you've got fully I1, and it's basically an isotropic dispersion. So your fibers are just dispersed everywhere. And this is an an orthotropic model if the fiber families lie in the same plane. And this has really been designed for arteries first and foremost, with two fiber families. This is what Holtz-Apfel and Gasser primarily worked on when they were developing this. And the idea being that if you have two fiber families, you basically got a statistical variation of the dispersion of these fibers about that main principal axis. The final model I'm going to talk about is a little bit different to the other two. This is the Bischoff anisotropic 8-chain model. This is based in the extension of the Arruda-Boyce 8-chain model that gives anisotropic behavior. And so the Arruda-Boyce model has a representative volume element with that's a cube describing the 8 fibers, the 8 polymer chains, sorry. And what this does is basically extend that out to a cuboid with normalized dimensions as material parameters. And so that controls the degree of anisotropy. So by changing the length of those dimensions, you change the length of your polymer chains and therefore the stiffness in each direction. The strain energy function, this is broken up into an entropic and repulsion terms. I won't go into this any further because it's quite in depth. If it's something that interests you, I'd recommend reading into the paper a lot more. It's quite a good paper. And you can get a bit more of an understanding of how these polymer chains are described. But very much the essence of it is that your degree of anisotropy is governed by these normalized dimensions of your representative volume element. As a quick final thing to talk about, I'm just going to run over the 2 different types of model calibration that are commonly employed. And model calibration is done since we can't directly measure the material model inputs. So we need to rely on parameter optimization tools to find them from the data set. So the way you do this is you have an initial material model. So, and then you run that in either an analytical solution or a single element finite element model. And you get a stress strain curve. And you compare that stress strain curve to your experimental stress strain curve, and you calculate an error variable. And that error variable is then fed into the optimization algorithm of choice. And from that, you then update your material parameter estimates and pass them through again. And you keep repeating this until you get to an acceptable level of error. If you don't have an analytical solution to the problem, such that it can't be described either by that analytical solution or by the one element problem, then you have to then think about using inverse calibration. And in this, rather than having that analytical solution or the single element, what you do is you replace that with the full finite element model of your test. And so what you do with this is that you'll have an initial guess as before. You'll write that into your input file. You'll run the finite element model. You'll extract your variables of interest. So let's say that's force and displacement. And you compare that force and displacement to your experimental. And then you'll update your material parameters until the error between the experimental and the FEA variables is reduced to an acceptable level. So this could be force displacement. This could also be your strain field from DIC, or any other variables that you can get from your FEA code, and you've got from your experimental data. A good example of this is for calibrating the constitutive model from a nano indentation test. You have your force and displacement data. You have your FEA equivalent, and you optimize over the data to get your constitutive model. So that's it for me today. I want to thank you for attending. I hope everyone found this informative. I'm happy to take any questions at this time. So yes, thank you. Just see if I can get this Q&A session going. So I have 2 questions on the chat. One from, I apologize if I pronounce your name wrong. Is it Xinping Gu? How to measure the compression strength of fabric sheet material adhered to a polymer surface? This is quite a difficult problem. What I would do in this scenario is, if you can't detach the fabric from the surface, I would basically, when I talked about that inverse FEA before, that is one way to solve this problem. Is you can indent you could perform an indentation test on that fabric, and then if you know the mechanical properties of that polymer below, you can isolate the polymer, and you've already calibrated that polymer using just a simple standard calibration as before. You can then basically put that into your FEA model and then optimize over the error between your indentation test data and your fabric constitutive model parameter estimates until you get a good estimate of that fabric mechanical response. Ideally, though, if you can isolate that fabric from your polymer, that is the best way to go. Inverse FEA is not as accurate as testing independently, and it's also a lot more lengthy process to do, both in testing and in your calibration. And do you send the recorded webinar to us? I am not sure of that. I can certainly check with our team and let you know whether we send that out. And if we do, you will be seeing it. Does anyone else have any more questions? I'm not sure. If you can't, if your microphone doesn't work or my settings aren't letting you talk, please feel free to enter in the Q&A section. But otherwise, if no one has any questions at this time, I want to thank you again for attending. Yes, this is the contact information for ourselves at Barist. We happy to help with any of your problems in the spaces we have expertise. And thank you very much for attending.